clusters in trajectory data today. So in my first lecture, I had this kind of examples of trajectory analysis tasks. And if we look at these first two, they are related to similarity. But in particular, the second one is more of a question of detecting clusters. So the question here is, what is a typical route? So here, for instance, I'd like to find maybe this part here, which is used by many of these birds. And that is a question of detecting clusters. A different kind of more global perspective is that we actually might want to do clustering on the trajectory. So really take all of the trajectories and group them based on the similarity. So let me just kind of show you a few examples of where we would like to, or where we are using these methods. If I have trajectory data, this is now of cars, we might want to reconstruct the underlying network. And at least for us, the first step that we're using there is first to find clusters or bundles, we call them, of similar trajectories, and they then often correspond to roads, and where these clusters then split corresponds to intersections and so on. So that is here the question of detecting clusters is useful. Another application that we looked into is this pigeon data here. So these are pigeons with a GPS. They live here and they like to be here, but researchers decide that pigeons should fly, so they release them here over and over again, and then the pigeon starts to kind of figure out where it should be going, maybe recognizes something here, flies that direction, then sees, home is down there, goes down. And then, okay, pigeon is home, rested, it has to go again here. And while doing that, the pigeon will learn more about how to actually get home fast, as we also learn in case we don't use our mobile phone to navigate.
Maybe you should say that in Germany this is a very popular recreational activity to have pigeons and let them fly and have races and this kind of stuff. It's actually, yeah, it's a strange hobby, but people do it.
Yes. So indeed, you don't do this here? I don't know. I also don't do it. And I think these guys also only did it for research. But you see that different pigeons actually kind of decided on different routes. You can also see, or that was actually kind of what we wanted to look at in the analysis, that eventually there's some kind of convergence towards a kind of last path, which it then always takes. But all of these questions are questions that where you can use a clustering analysis and do clustering first, and then based on that try to learn more about your pigeons or whatever your favorite bird is, or moving object. Good. So those are the two things I want to talk about today: detecting clusters first, and then the clustering. And here just two more examples of where detecting clustering would make sense. You might want to find commuting path or migration routes. Here is yet another example, a football example. So this is something Joachim Gudmundsson works on a lot, and therefore also I can take his nice pictures. So here that is more a question. Here you even are given some kind of additional curve, and you want to find the corresponding, you want to find a corresponding cluster in that data. Good. So schematically speaking, this is the setup that we have. So in particular, this question of detecting clusters is also an interesting question on in the case where you only have one trajectory. So this could be our trajectory, and now this path is essentially taken twice by that trajectory, and we would like to detect that. So the way we formalize this is, okay, by now you know me, we use the Fauché distance. Here we looked at pairwise distance. So we wanted that within a cluster, each pair of trajectories should be close. And we'll see more about that later, because eventually we switch to a different version because this one is too difficult. Then if we're detecting clustering, we do not want to kind of reuse the same part in the same cluster several times. And okay, this is, you can formulate as a multi-parameter optimization problem. And typically we want to maximize the length of the cluster. And this length, you have to be careful to define it appropriately. So length for us will typically be simply that there should be at least one of the trajectories in that cluster that has, or we want to maximize the length of the longest trajectory in the cluster, let's say it like that. As I said, we have now a multi-parameter optimization problem. So we're looking for a cluster with at least m subtrajectories of length L, and the Fouché distance should be below some value d. And in terms of results, and I want to discuss both of them today, since Martin today also did NP hardness proof, I wanted to top that, so I will show you too.
Tomorrow we'll see 3.
Oh my goodness. I will still have to update my slides for tomorrow. So deciding whether such a cluster exists is NP hard. It's actually hard to approximate below a certain value, below 2. But 2 approximation we can compute in polynomial time. So I would like to start with the NP hardness proof, and the reduction is from Max clique. So we've given a graph, and the question is there a clique of a certain size. So in this example, so for a clique I want to have all of the vertices pairwise connected. Here I have a clique of size 4. Yeah, so if I would be asking for case 4 here, I would find that clique. So now in terms of how do we now model this using, or encode this using trajectories? So we look at the problem of clustering k trajectories, and their length will actually be n. So if I have a clique like this, I will essentially have one set of points to encode the adjacencies of A, one code for B, one point for B, or one set of points for B, C, and so on. And the encoding that we have here is the following, and this is not yet trajectories, but just points and distances. I have A here. Everything that is adjacent to A sits here, and everything that is not adjacent to A sits down here. And the idea being that we'll have a trajectory that if I will have a trajectory that encodes A, and it will do the following. Since this is a set of points that encode A, it will go through this A point here. So, and then it will go simply through the points, either through the middle point if it is adjacent to that vertex. So for here this encodes B, and A is adjacent to B. So here it goes through the middle. And here too. And then for E is not adjacent to A, so here I'm encoding E, and here my trajectory goes down. And I do that for each of, I will have a trajectory for each of the vertices in the graph. So for B, it will go through B. And for instance, when I'm encoding D and its adjacencies, it will go down here. C and D and E. So those are my trajectories. And now my distance threshold that I will take will be essentially this distance. And what that means is, if I have a trajectory, so if you think of my first trajectory that went through A and then down here, if I want to include that trajectory into a cluster, then I'm only able to include trajectories in my cluster that either also go through A, so there's no other one going through A, or it goes through B, C, or D, because those just have kind of distance that is small enough. But E here, if I have a trajectory that goes through E down here, I cannot include it in a cluster with a trajectory that goes through A. If I do not want to include A in my cluster, I will be able to include everything else.
So Kevin,
yes.
Trajectory for D, if you go to that trajectory, you had like some bends in the middle. I did not understand for D. If you go back.
I will go back to D. Hopefully there's no mistake.
No. So that bend in the middle, I don't know what is that bend. Between D and DE. At the bottom, you have D and then DE, but there is a bend in the middle.
There's a bend in the middle.
It goes up and then comes back. I did not understand what is that.
Peak between.
Yeah, I see the peak.
Yeah.
And I'm now trying to think about why there's this peak. Is there some geometry why there has to be this peak? D. I'm also right now, I'm not sure why I placed it there.
Yeah, let's go ahead and
Yeah. I mean, this is also a somewhat schematic representation and not quite the geometry. But that is a good question. So this would be close enough, this would be close enough, but A and E is not close enough. And that in particular means, if I think of a mapping, so if I want to include A, this would be, the cluster would have to kind of move like this, which in particular means that if I want to include A, or let's say this would be now a cluster that includes A, B, C, not D, and not E. And what we see now is, so that corresponds to this clique here. And there is, so if there's a clique of size M, so if this is a clique here, then I can include A, B, and C in a cluster, simply because for the A curve, the B curve, so A is up here, and otherwise A is in the middle except for E, but for E, I mean B and C will also be either in the middle or down here, and so on. So there is this cluster if and only if there's a clique. So that means that it's as hard as max clique, and that in particular now also means that if I think about approximation, I can see since this distance is twice as far, so I would have to increase the size of the disk by a factor 2 to also, for instance, include E. So as long as I change the radii slightly, I can still encode the problem, and that in particular then also means that up to that factor, it's also hard to approximate. Yeah, so because the size of this disk, it has to be at least, let's say this is distance 1, so it will have to be at least 1, but I can still do the same encoding as long as the disk is just slightly smaller than, has radius just less than 2. Okay, so this problem is hard to approximate below 2, but it's very, so what you can see is that if I look at a slightly different problem, then that actually gives me a 2 approximation for my original problem. And the different problem that I'm looking at now is I want to cluster with a reference curve. So what that means is that I'm not looking at pairwise distance. So I'm not saying, okay, within a cluster every pair of trajectories has to have a distance below d. But now I'm saying there should be a curve in this there should be a curve which in my case is q, such that everything in the cluster has distance at most d to q. And then using triangle inequality, I know that the distance between p and r is at most twice the distance from to the center, and that means that if I now find a cluster, instead of finding a cluster where all pairwise distances are small, I'm finding a cluster where the distance to a representative trajectory is small, then that gives me a true approximation of my original problem. Now, if we look at this in terms of the free space, then it looks like this. So this is now the free space of, let's say I have one trajectory, of this one trajectory against itself. That in particular means that obviously the diagonal will be free, because if I have the same curve with the same parameterization twice, then I can simply, then it perfectly aligns. But if I'm now looking for subtrajectories that are similar to other subtrajectories, if I think of being here moving along the curve, and I'm now look at the subtrajectory corresponding to this interval here, then another subtrajectory is similar to a small distance to this one, exactly if there's also a free space here that I can traverse from the lower left, but now lower left relative to that subtrajectory, to the upper right. So if I can find this, you could say this set of free spaces, then that gives me a clustering with a representative curve. So if I can find these parts in the free space, then that gives me, then I know with distance in the free space with distance value d, then I know that with 2d I could also do find a clustering with the pairwise distances for, let's say, those three trajectories. And on the other hand, if there's a cluster with pairwise distances low, then obviously I can simply take one of the parts as representative and find then these clusters in the free space. So let me show you how this at least schematically looks like in terms of the trajectory itself. So I have this trajectory here. It's where does it start actually? I think it starts here. So I move a bit, and then this part here corresponds to this here, and then it connect the dots. Then it moves around, and at this point again it is close to this one that we were looking at. So then I get this white part here. It moves out again and in, and then I have it a third time, and that corresponds to this one here. And the way we can now compute this, and conceptually at least it's a fairly simple algorithm, is we're going to sweep the free space from left to right, but we have these two sweep lines where if possible I extend, so if possible meaning if currently I see this cluster, I'm going to extend the right sweep line to try to make it longer, and if at some point I don't see a cluster of sufficient size anymore, I will going to move this left sweep line. And what we want to make sure that at any event we want to have m curves from left to right. So I'm moving either, but if I lose this property of having m curves, then I'm going to move the left sweep line. I have a kind of slightly bigger visualization of that here. So I have two sweep lines right now. So m is 3. I don't have any clusters. So I'm essentially moving the left and right sweep line at the same time. Still no cluster, there are only 2. So at this point, so my left sweep line is here, my right one is just beyond. I have 3 curves here, one here, one here, one here. So now I'm going to move the right sweep line, and still I have 3 disjoint curves. And now, so now if I would move the right sweep line, this curve would end. So now I'm going to start moving the left sweep line again, and we start from here, and so on. Yes?
Wouldn't you find the same cluster 3 times when you do this?
I would find the same cluster 3 times, indeed. So the only extra information, so we need to maintain some extra information about, so that we can query whether there's still, so what we'll do is we're going to build a data structure on this part here, which we can query if I'm here, whether there's still a path to down there. And in particular, I also need to be able to query how far down I need to go. Because if my path goes down too far, let's say, let me take this example here. So if my path needs to go down too far, or up to here, then it means that here I will only want to restart slightly below that, because otherwise I get these overlapping subtrajectories. So I need to maintain that information, but at least in the, let's say, discrete Fisher distance setting, this is not too complicated. And the running time that we then get is n squared plus nm, so m was the size of the clusters, l the length, and order nl space. Now, I already briefly discussed this issue of if this goes down, where can I restart here? So that is, in terms of the continuous Fisher distance, the only kind of additional, or the main additional difficulty, because it means that if I want to include this curve in my cluster, and I have to go down, I have to go down somewhere onto this arc, then I have to carefully see that on this arc I don't start earlier before this one ends. So I have to start below that. And for that you'll have to look at a certain envelope of surfaces. So then the running time, so it's essentially the same algorithm, but because of this difficulty, the running time looks a bit more complicated, which just comes from plugging in whatever you get from working with these envelopes. But I don't want to go into more detail here. I'd like to just go back once briefly to where we now use this. So that was this map construction application. So the way we used it was first to run this on various values of epsilon to find many bundles in this data set. And then we have this huge set of bundles, and then based on certain kind of properties of the bundles, we select ones which we think are important, and add them to the network, and do that incrementally. And then when we see that bundles, that we for instance have bundles that would merge, then we add an intersection and so on. So I mean what we do on top of this is actually also quite interesting, but not part of the clustering. And then in this example we would reconstruct this network from this original set of trajectories. Are there any questions so far? Because now I'm switching to clustering. No? Good. So for clustering, I want to show you how we can get so first of all, I want to discuss how, at least I think, this problem should be modeled for trajectories. Then I'm going to show you an approximation algorithm to do center-based clustering on trajectories. I also show you the hardness. And then I have a few slides where I talk a little bit about more recent results. And depending on how much time I have, I might kind of go into detail for some of those. But at the very end, I want to bring this back to also the pigeon application. So the variant that I mostly want to look at is this KL center clustering. And that means, so it is like, the K is like in K center clustering or in K means clustering, meaning that I'm looking for K clusters. But we have this additional parameter L, and L tells us how complex the centers may be. So let me take a more schematic view on this. So center-based clustering, you know, on points. I mean, everyone knows k-means. Much of this, so not k-means, but k-center, k-median, you can also do in more general metric spaces. So our setting here is not k-means, but k-center, which just means that I want to find, for my given set of inputs, I want to find k balls, which such that for any of the input points there's a center of this ball. So I have a ball with a center, where for any input the distance to the center is low. So what I'm going to do is I want to minimize the maximum distance of a point to the corresponding center. So in k-means you have this, you're minimizing the sum of squares, but here we minimize the maximum distance. Now if you have points, then the center is simply also a point. And same here, if we have trajectories, then we also want the center to be a trajectory. The problem here is if you allow the center to be an arbitrary trajectory, then this trajectory could also have arbitrary complexity. And maybe let me actually draw an example, because I don't have it on the slide. So if my input, for instance, are trajectories like this, then you can imagine if I want to have a trajectory that is close to all of those, it would be somewhere start in the middle here. But here, because of this bump up, it would kind of move up here. It might move down there, move up here. So this could be a center for, if I'm looking at the case of I want to have one cluster for these three trajectories, this could be a potential center of a disk, in the sense that this has the maximum distance to this red curve over all of the trajectories is low. But you also see that this center picks up essentially any little piece of noise that we have in the input. And if you think of clustering as a way of summarizing your data, so of getting a compact representation, then obviously a center which is more complex than the input trajectories, or in this case, let's say as complex as overall input complexity, is not desirable. And that is a reason for the second parameter that we're introducing. It's up here already. The second parameter, where I say I have k, so I want to have k center trajectories, and they should have complexity at most L. Yeah, so k L center clustering, k clusters, but the centers should have complexity L. So an example of a special case, if L is 2, I would be saying, okay, I want to find line segments as centers. So then in my example here, K is 1, I'm just looking for one center. If I would say L is 2, then the center that I would be looking for would be something maybe like this. Or if I would say L is 3, I might pick up the largest outlier here still. So that is KL center clustering. This is an example for L is 2 and K is 1. In particular, K in the case of K is 1, this is a different geometric problem, or a specific version of this problem, and it's a minimum enclosing ball problem. So if you think of it in terms of points, if I say, I should have said K is 1 and L is, so minimum enclosing ball is not only K is 1, but also L is, let's say, infinity. Then I have the minimum enclosing ball problem, which is a problem that is interesting as such. And that is a problem that for points, I mean, finding the minimum enclosing balls for points is easy, but here for trajectories, as we'll see, is actually a difficult problem already.
Question.
Yes.
So for K center, if K is given and we know
Yes.
the center is the point, there is no ambiguity in the shape of a center, but in terms of trajectory, the shape of a center is a problem as well. So if we say L is 3, how will we decide that the center, what shape should have? I mean, the trajectory segments, how they are lying. Is it given, or we decide, I don't know how we decide?
I mean, that is something you're optimizing over. I mean, if you say L is 3, you know your center may have one bend.
I thought that we only work with the transformation. So with the shape, you optimize on the shape as well. Okay.
Yes.
Okay. So do we have
So-
some lines?
So in another example, if I have trajectories like this maybe, and I have trajectories that do, if this is my input and I say K is 2 and L is 3, then what I would like to have, will it? No, it will not. What I would like to have is something like this, then maybe this.
So it's the shape is a part of the optimization.
The shape is part of the optimization, yes. Yes.
Is this unique? Is it unique the center of the
No, the center is not unique, no.
Can
Yes.
you ever think to outlier to have this, for example, outlier
So we have not, we can add that to our list of open problems. We have not looked at settings with outliers yet. We have looked at the setting.
cover all unique cover all of
Yeah, so I mean, we've looked at the K median problem, where okay, it is kind of in terms of outliers a bit more resilient because you're not doing the maximum but the sum. But that we specifically kind of looked at settings where we say, okay, we also some of the trajectories may be outliers, and we want to do a clustering on the others. We haven't looked at yet. Plenty of open problems. Yes. Yes.
What happens when the data points on each trajectory is different? I mean, one of the trajectories, the points are very close to each other.
Mm-hmm.
And in the next trajectory, they have a different distance.
So it's a good question. That depends on that also depends on the distance measure that we're using. So if we have, if we use if we are using the Fouché distance, and okay, I have this densely sampled trajectory, and I have another one which is maybe less densely sampled. then, I mean, the Fauché distance sees these as polygonal curves. So the sampling, the difference in sampling, I think doesn't matter much here, because I would still find this, let's say LS3 finds the center. It gets problem.
You said that at most data points in each trajectory.
In each of the centers. In the centers. So L is not yeah, maybe data point is also a strange name for these centers, for these points, because they're not really data. I also said vertices. So this is only about, so the center should here, for instance, have complexity 3. And obviously, I'd hope to, in this way, represent trajectories with many more data points. Yes. I think, so part of your question can also be related to the distance measure, because if I use discrete Fauché distance, then of course I will run into problems in several ways. First of all, the two original ones here are not very similar, because for this one I only have those points to map to. But also when clustering, in particular in the setting of where I restrict L, when I say I want to now cluster using discrete Fauché distance or dynamic time warping, slightly strange things happen. Because if I here use LS3 and I would want to use this point, that point, this point, it means that all of these blue points in between will have to decide to go through to this and that point. And it gets even stranger with dynamic time warping, because let me just show that example. I can run into settings where I have inputs like this. And where my center now, so I would like to have a center that sits here, obviously. But with dynamic time warping, I might end up with a center which picks a point here, picks a point here, picks a point here, because then everything here nicely matches here, everything there matches there. So with depending on a distance measure, you have to be careful with sampling. But back to your original question, this L is we can place them anywhere. So it doesn't need to be on one of the original data points. Good. I'd like to discuss the following results. NP hardness. In particular, it's also hard to approximate within some factor which is between 2 and 3. If we just look at the minimum enclosing ball problem, then it's hard to approximate within anything smaller than 2. And then I also want to show you a polynomial time 3 approximation for this problem. I will also show you a 2 approximation for the minimum enclosing ball problem, but that's less interesting, as you will see. I will actually start with this, and I will start with the minimum enclosing ball problem. And this is actually very similar to what we already had seen when we were trying to find clusters. So if this is my input, then let's assume C, so this was my input, C is now, let's say C is a center for a minimum enclosing ball and the radius, so the optimum radius that we can get is R star. Then simply by using triangle inequality, if I take any of the input trajectories as center, then, so here I took Q as center, then what we get for any other trajectory, so let's say for P, the distance from P to Q is at most the distance from P to C, and then the distance from C to Q, which together is at most 2 times the optimum radius. Which means that the minimum enclosing ball problem we can very easily approximate in actually an optimal factor of 2, but algorithmically maybe not the most interesting result. I'm showing this because now we'll be using the same idea, underlying idea, for the more general problem. So the algorithm that we're using is an adaptation of Gonzalez algorithm for clustering, for K-center clustering in metric spaces. But we have two differences that we have to deal with here. So for one, we do not require the center will not necessarily be one of the inputs. And even worse, the center actually cannot be the inputs, assuming that the inputs have large complexity, because we have to use center curves which have complexity at most n. And the algorithm now proceeds as follows. We pick any of the input curves as base for the first cluster center. So let's say this is the one we picked, P1. Now P1 is not a suitable cluster center yet because the complexity might be too high. So we're now going to simplify P1. So we're going to get Q1, and that will be our first center. Now, next within the input, we'll look for the curve which has maximum distance to any of the current center. So that currently is just maximum distance to Q1. And we'll take that as base for the next center. So that in this case might be this P2 here, because there's a large distance here. I'm taking that as a base for the center, so I'm going to simplify P2, getting Q2, and so on. And in my case, K is 3, so now I would stop. So this is what my algorithm produces, and what I would now like to show is that this is a 3 approximation. For this, let's have another look at, so we have these PIs. Those were the base for the centers, you could say. And we have the QIs, which are the actual centers that we picked. And if you think of this process of adding one center by, and then the next center and so on, and I look at the radii, the maximum radius of a cluster that I have during this process, so initially I just have one cluster, then during this process the radius decreases. And in particular it means that if I now look at, so I have I smaller j, so I'm looking at a center that I already have, and I'm looking at one of the future trajectories that I'm going to use as a base, then the distance here is at least the radius that we had just before we picked this pj, and because these radii are decreasing, if I look at then the radius at k, so when I'm finished with my cluster, this will be even smaller. So that in particular means that these distances qi pj are lower bounded by the radius that I end up with. So now let's see. So what I'm doing now is I'm looking at the P at P4 here, and P4 would be the base of the next center that I would choose. I mean, my K is 3, but now I kind of assume I do the algorithm just one step further. That gives me this P4 here. And that will be used in the analysis. So if I look at an optimal clustering, then since I now also included P4, so I have one more curve than I have clusters, it means that by pigeonhole principle, one of these PI will have to be, two of these PI will have to be in the same cluster. In my example here, it's P1 and P4, which are both in this, would be both in the cluster of, and this would be one of the optimal centers, Q prime. But if we now use triangle inequality, what we get is the radius that our clustering had, which is this RK, so the radius after adding the k's center. As we observed up here, it is lower bounded by the distance from of any qi with pj, which I can now split, so I can apply this to p1 to q1 and p4. So then I get this is lower bounded by using triangle inequality. I plug in q prime, so I can go from qi. So the qi would be, so q1 in our case would have been this zigzag version of p1. I can go from q1 to p1, then I can go from p1 to the center, and I can go from the center to p4. Now I know, so R star is now the cost for the optimal clustering. That means that since P4 is in the cluster of Q prime, this is bounded by R star. Since Pi is in the cluster of Q prime, this is bounded by R star. And since Qi was a simplification of Pi, and if I now assume, if I use an optimal simplification, then since this is Qi is a simplification of Pi, the best simplification of Pi, in particular this distance will be at most the distance between Q prime and Pj, now I'm switching, between Q prime and Pi. So what I'm saying is that if I had an optimal simplification for P1, Q prime would also be a simplification of P1, but since the one that I used was optimal, the distance from P1 to the center will be, the distance from P1 to its optimal simplification will be lower than the distance from P1 to the center. So that gives me a third R star in this analysis. So that's why the quality of the clustering that I computed here, or the algorithm computed here, is at most 3 times the optimal. So that means we have a 3 approximation. So next I'd like to look at hardness. And the reduction here is from shortest common supersequence. So we have a set of sequences, S1 to Sn, and they are over a binary alphabet. And I now want to compute the shortest sequence such that any of the input sequences is a subsequence. And an example would be, if this is my input, so I have the sequence ABB, BAAA, ABA, then a possible shortest sequence, supersequence would be ABBAAA. Of course, ABB is included here in the first 3 letters, BAA is included here, and ABA is, I can take this A, one of the B's, and A here. So this is a supersequence of all of 3 of these, and this, if it's the shortest, then it's a solution to this problem. This problem is NP-hard, and now the idea of the reduction is that we, for each of these input sequences, we will have a curve, and then the center that we're looking for will correspond to a supersequence. And essentially what we now need, if you think about this problem, so we'll have the center that we'll have will be a longer sequence. So there will be things on the center not mapped to, so one step back, so I'm encoding these sequences by polygonal curves, and essentially what that will mean is that I will have some location where for A and some location for B, and depending, the intuition is I want to move from the location from A to the location of B, back to the location of A for this one, and so on. And then the supersequence will move between those locations more often, in some way picking up all of these patterns. But now obviously the difficulty here is that the supersequence will also include parts which then, if I want to map, let's say ABA and ABBAAA, then the parts in the supersequence that I don't want to use, those I will have to somehow map to other parts of the input that I create. So, and okay, this is slide just about the supersequence. So if at some point I get a center, so let's say I have an algorithm that computes a center, and it moves. I'm now in 1D. So I'm looking at 1D. So my center can actually only move up and down, and I use this third axis just to kind of illustrate time. If it moves down further than, if it moves down below -1, then we interpret that as A, and if it moves above 1, we will interpret that as B, and everything else we will want to ignore. And the way we do this in the input sequences, so if I have in my input an A, what I'm going to do is I will have one spike down here which will force the center to go down. So this spike enforces that the center somewhere has an A, which means a vertex that is goes sufficiently far down. The center might also have other parts which lie somewhere between -1 and 1. And to allow those parts to be ignored when doing the matching between the sequences, we encode an A in a sequence by having lots of additional spikes here, which allows any additional A's or B in the super sequence to be handled by this. Yeah, so the super sequence to pick up this, if my distance is 1, would have to go down at least to here. Now it might also go up and so on. So B will enforce it to go up here. So if I now have a sequence that goes, let's say I have my input sequence is just A, and my super sequence will be A, B for some reason, then it will go down, and I will want to go down and up to 2, up to here, and maybe there are even many B's, but all of these B's I can pick up by these small wiggles that I include in my A gadget. So I have more examples. Let me show those. So this is now the example that we previously had. S1 was ABB. The super sequence that I wanted to have is ABB. That would work as ABBAAA. So ABB I encode by wiggles, down, wiggles. B by wiggles, up, wiggles. And another B by wiggles, up, and more wiggling. And now I can map ABBAAA. So the A I can simply map to this first spike of here. Then the B's, the two B's that I need, I can map to those two spikes. And then I have these 3 A's that the super sequence uses additionally, but those I can simply map to the wiggles that are over here. And then similar example, the second one was BAAA. So then my super sequence first had an A. I would like to ignore that. I can map it to one of these smaller up and downs. Then I'm going to use map this B to the B, and then the rest. Then I can map the other B to just one of these small ones and 3 A's. And this is then the third one. So what we have now is, if there is a super sequence of a certain length, then there's a center curve which consists of at most 2t plus 1 vertices, and the other way around. If I can find a center curve which has the radius 1 in the setting, then I can read off the super sequence. So the center curve has complexity 2t plus 1. I can find the super sequence of length t. And that means in particular that we can reduce this shortest common supersequence problem to the 1L center problem. So we don't even need to use higher k here, it's just with 1. And actually we can also do the minimum enclosing ball, so we can also kind of set this parameter L very high. So this gives us, if you again look at these gadgets, you can change, you can vary distance, you can vary your radius to some degree, up to a factor 2. So that gives us actually a 2 approximation. In 2D we can do the same construction but somehow use the space more effectively, or place the gadgets further apart by kind of having a 1D space circular here. So the idea again is the same, but instead of now getting being able to show that we cannot approximate within a factor smaller than 2, we can show something slightly higher than 2. Ideally, if you go back to our approximation algorithm, ideally we would like to show that it's not possible to approximate within any factor smaller than 3, but we are not able to do that. So we first thought, okay, if we can increase this slightly by going to 2 dimensions, then we go to 3 and general d dimensions, but somehow we were not able to exploit the higher dimensions. I'm not sure whether that is simply a property of 2 dimensions or simply a property of missing intuition about the higher dimensional cases. I would hope the latter. Good. I would like to just show you an overview of our most recent results, and for that I have to briefly introduce one more problem. So we were looking at the KL center problem so far, where I minimize the radii of the cluster, and now the KL median clustering problem, I'm going to minimize the sum to the corresponding centers. And otherwise the problem stays the same. So I just put this table in fresh from the paper, and fresh meaning that we also just finished it. So yesterday I updated my slides. So if you want to read more about it, you can either wait for a short amount of time or simply ask me for the paper. So what I would like to highlight is, so a very interesting question is not simply using Fouché and discrete Fouché distance, but to use dynamic time warping. In particular, so dynamic time warping makes more sense in this median setting. So generally, I mean, you can combine obviously median and center with your favorite distance measure, but dynamic time warping, you're using sums, then that naturally combines with a sum over the clusters. So there, we can also show that it's NP hard, but also others very recently showed that it's NP hard. So here our main improvement is to essentially in dynamic time warping you can choose, if you use your distance, your Euclidean distance, you can choose your exponent. Whether typically you would use a squared distance, and that is handled, or just the regular distance, which corresponds to this case here. So this is how the exponent, and this means then that I'm going to use the square root. We generalize that to arbitrary ways of weighing an individual distance. Algorithmically, there's not many results, and the difficulty there really is the missing triangle inequality. So we don't really know how to make progress in that direction right now. Well, but let's see. Then what I showed you for the center, essentially much of this with a little bit of extra work generalizes to the median problem. And let me also show the second slide in terms of algorithms. So actually the hardest results here are more, I'd say, more intricate than the algorithmic solutions that we found so far, because all of the algorithms that we have are very much brute force.
Did
Yes.
you say that the same method that this subsequent sequence method is used for proving the NP hardness for the 1 million?
Yes, it's essentially the same ideas, just that you have to, you have to do the encoding you have to first blow up the strings a bit to make sure that in terms of weight everything works out. And so there are small changes, but I think the main change is that the analysis is more difficult. Yes, so I should wrap up. So these are algorithmic results. We can say anything. So the 3 approximation I mentioned, if k and l are seen as constants, then you can brute force your way through the problem. Is that actually here on the slide? So we also have an exact. That's actually not on the slide. We also have an exact algorithm, but that has really bad running time. But as you see, so the center problem, you saw the 3 here. Here we started with Gonzalez algorithm, but the median problem obviously also in metric spaces has been studied before, so there are algorithms there which we can base our algorithms on. All of the 1 plus epsilon approximations essentially build on finding first some approximation, let's say the 3 approximation, and then placing grids around the vertices of the 3 approximation, and then testing simply all combinations. Good. So those are the results so far. I already talked a bit about the pigeons, so let me just show you this one. Yes. So here the analysis question that we were looking at, is there a convergence towards a final route? So, and then we did a clustering, found main clusters, and then tested whether the final route would fall into essentially the main clusters, and they did. So there's kind of some indication that there's actually a final route for each pigeon. But we also observed that, so another analysis that we tried to do was to see, can we use this to identify pigeons? And that was not possible because some of the pigeons simply used very similar paths at the end. This can also be used for visualization. This is just a small example, which, okay, I mean, it just shows a clustering as previously, but this is drawn from a database that has worldwide animal data, and you could imagine that to give you a quick summary of various data sets, that instead of showing the tracks, you can show a clustering for each of the data sets. Let me just put up the slide with open problems. Dynamic time warping approximation algorithms, that's a very difficult one. If you have a lot of intuition about higher dimensions, then it would be nice to improve this approximation factor. In terms of problems that maybe haven't been studied that much yet, so I don't know how difficult open problems there are, is if we use a weak Fouché distance. But if you do that, you have to also check the work by Harpellet and Reiche, because they have some positive results. But in terms of lower bounds, there's quite a bit open. And also there's this middle curve problem by Higab Ahn and others. Actually quite a few of recent speakers here, so Carola Wenkes on that paper, and Helmut Alt and Kevin Bokhin. They gave algorithms for this problem, but did not discuss lower bounds. And that could be kind of an interesting problem to study. They are, well, now I have to say, I guess they're NP hard. So it is more in terms of, so they have algorithms where the number of trajectories also show up in the exponent. So, I mean, you can think about hardness, but you can also think about conditional lower bounds, where you show, so they have running times of n to the, let's say, some kind of 2k, and then you could try to show that that's a lower bound of n to the 2k, or show a lower bound of n to the k, unless your favorite hypothesis fails. That was more kind of the direction I was thinking of in here. NP hardness they probably covered, I'm not sure. Good, thank you.
Question? Anybody else except you? Okay, please ask.
What's the simplification algorithm that we use for finding the density space?
So we had a look at several ones. So you have the option of using an approximate simplification algorithm, and then your approximation factor simply goes up. So I think you could, for instance, but essentially all of the so in terms of approximation algorithms, the work that is needed here is from the Gibash et al. The stabbing disk with lines or line segments paper, because looking at a vertex constraint version here doesn't make, vertex constraint here is not good enough if we want to make a claim about optimal cluster centers. And in particular, local versions will not work here if I want to overall say that these are, if I want to approximate optimal cluster centers. So this is more based on this line stabbing by Gibash, Snowing, and this you probably know.
What is the result exactly? Approximation for each case of the simplification versus simplification? What's the current simplification for the
So I actually would have to look into the paper because it was a bit intricate, because they didn't exactly show what we needed to have, so we still had to put in some extra effort. They essentially had, essentially we could.
and the black box simplification, that's enough for approximation?
Yeah, so we use exactly. Yeah, you answered your question. Perfect.
So actually, this is quite a nice technique, this reduction to this problem of the sequence of sequences.
Yes,
And,
thank you.
What's wrong if you go to the 3 dimension? You mentioned that you didn't have the map. So you can just do some similar things.
You can do similar things in 3 dimensions. Let me go back to the slide here. I not in this presentation. I have more slides on this if you want to discuss it further. But the problem, the question in terms of our approximation factor is always there's kind of this intended radius, you could say, and then you kind of see how far, or the tight radius, and then you look at how far can you blow up the disks so that combinatorially nothing changes. So even with this larger disk, everything still behaves as intended. And our initial idea was to say, okay, we can do this in 2D like this, and in 3D then we take a tetrahedra, and then the path kind of visits and so on. But somehow in terms of the disks intersection there, it didn't help in terms of improving. Actually, I think what we got was worse than in the 2D case. It didn't help. So the disks intersected in a way that we ran into problems proving anything that works better.
I have a question as well. So the data for the pigeon or the code for tree approximation is available somewhere online, or?
Yes, there is an R package with this algorithm and also some kind of heuristics to try to get better centers, because obviously, I don't know, I find this with the 3 approximation slightly funny in the sense that, okay, you get a nice clustering, but if you now want to use the centers, the centers are just kind of original trajectories simplified, so it's very obvious that, let's say in the case of one cluster, if you go to a biologist and say, okay, I can solve your problem in a 3 approximation, I'll just take one of your input trajectories, they might not be happy. So we have done some heuristics to try to kind of get better centers there. That's all in an R package. In that package there's also, the pigeon data is also available somewhere else, but we included the pigeon data also that you can kind of get started with.
So if you Google it, you can find it.
I hope you can find it, otherwise you'll ask me. But it's on GitHub.
Excellent. Thanks. Yeah, another question.
Do you have any idea of what the problem is, the importance of basis?
Is it importance of trajectories are different? So I haven't thought about that version yet. I'd assume that my first step at least would be to look into, again, what is known in metric spaces. That seems like a very natural variant, which hopefully somebody already considered, and then take that as a starting point to then design algorithms for trajectories.
I mean, very easy ideas resolve is that somehow you can just repeat the trajectory, but not on the same place, but just a little bit further, and so that the magnitude of it gets high, and it plays more role in the results, and then use the same technique. So you don't need, if you want to put some weight on the trajectory,
yes.
you don't necessarily need to.
So for the in particular for the median setting, that would work. For the center setting, having the same trajectory several times will not change the clustering. So then you would, I guess, you would want to
just a little bit further somehow to make it a new trajectory so that it plays a role.
Yeah, but what I meant, and maybe I'm wrong. In the median, yes, in the median, yes. Okay, yes, I completely agree.
Thanks.
Yeah, thank you.